Okay. All right, let's talk about another thing I'll just mention is, so we call it, we developed the weak form, or another name is the variational form, and if you look at it like that, then it might, this is what I was saying at the very beginning of class, right? When we start with Hamilton's principle, we get a variational principle from the get-go. So it's if you do have a problem that has, it's essentially just a mechanics problem where you can write down a conservation of energy, potential and kinetic energy, then you can just basically use Hamilton's principle directly to develop the variational principle. Because, just like in when we derived our equations, we ended up with like terms like this, d dx of del u. But then we used integration by parts to get the del u off of that thing so that we could put it over there and invoke the fundamental limit of the calculus of variations. But here we don't have to, because ultimately we're going to choose del u to be some ansatz, some basis function, right? So Hamilton's principle is a very useful way to directly develop a weak form if you have, if it's a mechanics problem and you can write down statements of kinetic and potential energy. So now let's talk about the bilinear form. The weak form will contain two types of expressions. Those involving del u and u, and those involving only del u. I really apologize for my handwriting. Not that it's ever great, it's really bad right now because the pen is like a centimeter off from where, where the lines are appearing. Okay, so what we'll do is we'll group. So we'll write B of del u comma u equal to the ones involving both. So I'm just grouping terms from our weak form. So then with this, we can write the problem. We can write the problem is stated as find u This is known as the variational problem. So in mathematics literature, a lot of times you'll see this type of problem statement.
In the second equation, so there is a term del u. What is the term?
Del u f of x dx. Yeah. Yeah, this is. All right. The functional, B del u is said to be bilinear if these two statements are true. B is symmetric if that statement is true. Gosh. There we go. Gosh. All right, we're almost done. If it's bilinear and symmetric, then B del u is equal to 1/2 del B u, and L del u is equal to del u. And so this is one reason why I like to use for my test function del u, because we've already introduced the del operator. Like we kind of know what it does and how to use it. And so, basically if B is bilinear symmetric, then I can move the del operator outside, right? And basically just say I have a function B that's u, and then I can take the variation of that to recover this thing, right? Whereas, like a lot of times in mathematical literature, you'll just see the bilinear form stated more like this, where you have u and v, where u is called a trial function and v is called a test function. But all of this originates from calculus of variations, and so that's why I like to use the del u operator. But with that, we have 1/2 del B u minus del L u, And then we can define that to be equal to del I of u, and that has a stationary value, right? So then we can restate the variational problem as IU equal to 1/2 B U U minus L U. And so restating the variational problem in this way basically is saying that, you know, our goal is to find a stationary value of IU. And so, you know, if you go back and you were to look at, like, when we originally derived Hamilton's, whenever we originally used Hamilton's principle, right? If you go back and you look at the terms, I think you would see things that start to look right, because think about the kinetic energy, right? It was 1/2 rho v squared, right? So you can think of that again, it's like 1/2 VV, right? And so that original statement of energy, kinetic minus potential energy, basically the minimization, you know, you could recast it in this kind of form where basically minimizing the energy gives you, you know, the minimum of the energy gives you ultimately the conservation equation, the conservation of momentum, right? And then if we plug in approximation spaces for those, then we can get an approximation to the solution. So, I'm tired of writing 1 centimeter off of where I'm writing, so I think we'll stop there. It's a good place to stop, right? So next time we'll work a problem, right, using the Ritz method. Using the Ritz method in terms of like this setting, okay? And then from there we'll move on, because understand that like this problem is equivalent to the problem above, like B del U U minus L del U. Those two problems are equivalent problems, right? So we can say we're either going to minimize or find the stationary value of this integral functional, or we can solve the variational problem. Find seek a U such that B del U comma U is equal to L del U. Either one of those is, you're doing the same thing. You're solving the same problem. Okay? So we'll work this, for the Ritz method next time, and then after that, we'll introduce discretization technique, and then we just apply that over elements, and then we have the finite element method.